This is the third and final video for thermochemistry. So far we have discussed heat transfer. Remember, that's conduction, convection, and radiation. We learned about heat capacity of a substance as well as specific heat of a substance. And now we're going to focus on heat transfer within a chemical reaction. Before you learn about heat change that occurs in a chemical reaction, we need to define a few terms. The first term you need to know is called the system. It is a specific part of the universe that is of interest in the study. So you can see that we've got 3 bottles here. The first bottle, this one, is called an open system. It's open because we have, you can see it's saying that it's water. Water can go in, out of the bottle and into the bottle. So it's open. So we have an exchange of mass and energy. Energy can go in and out through the walls of the bottle. So the system could give out heat, or it could take in heat. The second system is called closed. It's closed because it has a cap. So the mass cannot go in or out, so it stays the same. The only thing that can be exchanged here is the heat. So the heat can go into the system or out of the system. The third bottle represents an isolated system. Isolated means that there's no mass going in or out, and there's no heat going in and out. So there's no exchange of anything. The second term that you need to know is surroundings. So everything that is around the system is called the surroundings. So we have established that heat can either go into a system from the surroundings, or heat can go out of the system to the surroundings. So we call the process that gives off heat is called exothermic. So that is the transfer of thermal energy or heat from the system to the surroundings. So Q, which is heat, has a negative value. So I've got 2 examples here. The first one, we've got 2 hydrogen gas molecules plus oxygen gas gives us 2 water molecules plus energy. So this reaction tells us that along with the product, we're giving off energy. The second example is water, or gaseous water can be converted into liquid water plus energy. So again, we're seeing the products plus energy. So these reactions are giving off energy. So if we were holding a test tube with a reaction or an exothermic reaction inside of it, we would feel the test tube get hot. So that's exothermic. Endothermic process is the opposite. So an endothermic reaction needs to absorb energy in order for the reaction to go to completion. So I've got 2 examples. First example, we've got energy plus 2 mercury oxides gives us 2 mercuries plus oxygen gas. So you can see that energy needs to go into the reaction in order for the reaction to work. The second example is energy plus solid H2O gives us liquid H2O. So solid H2O is ice, right? And if I add heat to it, I get water, liquid water. Alright, so that makes sense. If you heat up ice, it turns to liquid water. So that's an endothermic process. So remember that Q has a positive value because we're adding heat to the reaction. We can measure the amount or the heat of reaction. So heat of reaction is also known as enthalpy, and it's represented by a delta H. So right here. Alright, so the definition of enthalpy is that it's the energy released or absorbed during a chemical reaction. So basically, enthalpy is the difference between the potential energy of the products and the reactants. So if we know the heat of the products and the heat of the reactants, we can find the heat of the reaction. So delta H of reaction equals the heat of the products minus heat of the reactants. So remember we just said that endothermic reaction, heat is absorbed. So we know that the enthalpy, or the heat of the reaction, is going to be positive. Exothermic is when the reaction releases heat along with the products, and delta H is going to be negative. So now let's talk about energy diagrams. So we can use energy diagrams to illustrate what's happening in the reaction. So if we look here, we've got potential energy increasing along the y-axis. We've got time increasing along the bottom. So if we start out with our reactants, A and B, we're at this energy. The reaction goes, so we can see this part means that the reaction is occurring, and then when it's done, we're end up here. So you can see that we started at a higher energy than we ended up at. So the difference right here is our delta H, or heat of reaction. Let's take a look at the energy diagrams of an exothermic reaction versus an endothermic reaction. So let's start with the exothermic. So exothermic, the product is going to have less energy than the reactant. So we look at the diagram here. We've got the energy that the reactant starts at, energy change that happens during the reaction, and then we have the energy of the products. So you see the energy of the reactants is higher than the energy of the products. The difference is our heat of reaction. So for an exothermic, we're giving off energy, so we could put plus energy here. Alright, so that's the energy that's been given off. For endothermic, we can see that our reactant starts at a lower energy than the products. So we get our delta H is here. Alright, so the products have more energy than the reactants. We can use an energy diagram to actually figure out the value for heat of reaction. So if we look at the energy diagram here, we know that our reactants start at 50. The reaction occurs, and then our products end up at 100. So, by using our formula, the heat of reaction is equal to the heat of the products minus heat of reactants. So products are 100, reactants were 50. 100 minus 50 gives us 50 kilojoules. So this would be the heat of reaction. So we can tell if the reaction is endothermic or exothermic by the amount of energy of the product. So this energy diagram here is endothermic because we have gained energy, and that means the products are higher up in energy than the reactants. So we can calculate the heat of reaction either by looking at an energy diagram, or we can also look at the heat of formations for the reactants and the heat of formations for the products. So to do that, we still use our formula here, but this time we're going to have to figure out what the heat of the reactants is and the heat of the products. So to find the heat of the reactants, we add up the heat of formations for each reactant, and then to find out the heat of the products, we add up the heats of formations for each product. Alright, and so if we have, make sure that if you have a coefficient in front of that molecule, that you need to multiply the heat of formation by the coefficient. So let's look at an example. For this example, we're given the balanced chemical equation, and we're also given the heat of formations for each molecule in the reaction. So let's determine the heat of reactants first. Alright, so for the reactants, we're starting out with CH4. So we look at, this is the heat of formation for CH4. And since there's no coefficient in front, I know I only have one. So I'm going to do negative 74.8. And then the second reactant, we've got two O2s. So heat of formation for O2 is 0. So 2 times 0 is 0. So I can add these up. So I get negative 74.8. So that's our heat of formation for the reactants. So now let's look at the products. Alright, so for our products, the first one we've got is carbon dioxide. Heat of formation for carbon dioxide is negative 393.5 kilojoules. Second product, we have two waters. So this time we're going to go 2 times negative 241.8. And then we're going to add that up. So our heat of the formation of products is negative 877.1 kilojoules. So now we can use our delta H products minus delta H of reactant. It gives us the heat of the reaction. So when you subtract 877 minus negative 74.8, the heat of the reaction is negative 802.3 kilojoules. So it's products minus reactants. We also know, since the heat of the reaction is a negative number, that the reaction is exothermic. So it's going to be giving off quite a bit of heat. To classify reactions as endothermic or exothermic, just remember that endothermic has a positive delta H, and exothermic has a negative delta H. So if we look at these different examples of reactions, and you look at the delta H values, we know that if it has a negative number, it is exothermic. The rest of these are endothermic because they have a positive number.